All right, looks like we're good to go. Hello, everyone. Welcome. I hope you enjoyed your lunch. So my name is Bill Magro. I work at Intel. I'm a chief technologist for high performance computing, and I lead our HPC in the cloud efforts. And today I'm going to be talking to you about high performance computing in the Amazon AWS cloud. Matt McKee, who's director at Rescale, is going to be joining me on stage and for the second half of the talk. And what we're going to talk to you about today is really why are people looking at the cloud for HPC? What are the capabilities from the silicon level up to enable the infrastructure, ultimately a platform level interface? And then what are people doing on top of that? How do you make it easy to access HPC in the cloud to get productivity out of the cloud? So this is a mandatory Intel legal notice. Says a variety of things. You see it anytime Intel speaks. So first, I'll get us going and talk about Intel. Fundamentally, Intel powers HPC in the cloud because at the heart of the cloud are Intel technologies, such as Intel Xeon processors. And I'd like to tell you a little bit about what we do at the bottom up, and then how we're working with the ecosystem to enable easy access to familiar interfaces, familiar platforms for you when you're trying to do high-performance computing in the cloud. But before I do that, I need to talk about what is HPC. Sometimes if you ask someone what is HPC, they'll say it's using supercomputers to solve the world's largest problems, and they'll define it in terms of the infrastructure. Other people might say HPC is all about the problems you're solving, such as the domains that are on the screen here, life sciences, doing personalized medicine, cancer research, or gene sequencing for personalized medicine. Financial markets run on HPC systems, so risk analysis and program trading. A lot of our energy and the efficiency with which we can extract energy, oil and gas from the planet comes through high-performance computing, seismic to discover where it is, and then reservoir management to maximize the utility once you've drilled, and how do you manage that reservoir and pump and get the most oil out. Our weather is forecasted with high-performance computing systems. Scientific visualization is done that way, and so on, all the way up to national security. But when I think about high-performance computing, I don't think in terms of the infrastructure or necessarily in terms of the workloads. Instead, I think in terms of what is the activity that you're doing. Ultimately, you're trying to use a high-performance system to generate insight. You're trying to understand something that you didn't understand before, whether it's mining through massive amounts of data to gain an insight, as is done commonly today with artificial intelligence, whether it's predicting the path of a hurricane and knowing that it's going to take an unexpected turn so you can evacuate and save lives and minimize property damage. These are valuable insights that are delivered through this activity. So high-performance computing to us at Intel really comprises three things. One is a problem where the purpose of the activity is insight. The second thing is the fact that it's a computationally demanding problem. If it weren't computationally demanding, we couldn't legitimately call it high-performance computing. The third thing is that as you apply more resources and you do it appropriately and intelligently, you get a more valuable result. And this is where cloud comes into it. So this is a picture of a couple different styles of high-performance computing. If you were to take that view that high-performance computing is all about applying a supercomputer to the hardest problems, you would miss a tremendous opportunity in HPC. You'd miss the opportunity to see how cloud fits into that picture. So on the left is kind of the traditional view of high-performance computing from an infrastructure perspective, where we have a bunch of uniform resources. They're tightly coupled to each other. They have a very low latency network, very low jitter, high bandwidth. Your processes are all placed perfectly together. When you do that, you can actually start to scale problems up to massive scales. And that is what's needed for doing things like climate modeling and weather prediction. It is needed for things like doing a car crash simulation and understanding how a car is going to perform before you build it, understanding how it's going to perform in rollover tests for occupant safety. But leading up to that point, when you're ready to do the big simulation, oftentimes you're doing a lot of small simulations. So think of the car example. Someone is working on, say, a headlight where a designer has said, I want to get a more aggressive look, and is trying to put an angle into the headlight. Meanwhile, someone else is concerned with fuel efficiency and saying, hey, if you put that angle in, you're going to increase drag. So the engineer ends up with these many requirements and needs to search through a lot of designs to find the best case or the best design that will meet all the needs. Similarly, someone else could be working inside the cabin trying to find a material that will minimize occupant injuries during a crash. Now they're studying the behaviors of foams or other things inside the cabin, doing a small simulation when maybe there's an impact to the knees or an impact to a driver from an airbag. How do we design a safer car? All of those simulations, all that design space exploration is actually something that can be done through a massive, what we might consider high throughput type environment. And this is where the cloud comes in, and comes in really strongly, because even though you're applying a massive amount of resources to a problem to get a more valuable result, the insight of which design I should follow, you're doing it through a collection of smaller simulations that don't have the same characteristics and thus don't have the same requirements on the high performance computing system. So if you imagine on the spectrum of workload demands, there's a whole range of workload demands that a supercomputer can satisfy. And there's a subset of those that the cloud can satisfy. And by being intelligent about what you put where, you can actually get more done and improve your productivity. So this kind of informs why people are looking to the cloud for high performance computing. And the second one in the middle on the top there, managed demand surges, is an example of what I was talking about. So in a well-publicized example a few years ago, Western Digital, which creates hard drives, was trying to design the optimal head for the hard drive. And they needed to do this type of design space exploration. So they used Amazon Spot instances and were able to spin up almost 71,000 cores and do the design space exploration, trying 1 million different simulations. And then they were able to achieve in 8 hours what would have taken 30 days on their on-site computer. They ended up freeing up their on-site supercomputer to solve the hard problems that demanded it. And meanwhile, their engineers, who would have been waiting a month to make a decision, could now get the data and make a decision in days. This is an example of intelligently using the cloud to augment the systems that you have on-premise. Similarly, no matter what system you buy on-premise, the economics of it can be quite great. But your supply is static. Your demand for compute is highly variable. And in fact, when we talk to market analysts, they say that typically they see a 25% plus backlog of demand on high performance computing systems. Now the reality is that most engineers, most scientists will actually stop submitting jobs to a queue when the backlog gets to about 25–30%. My own background is as a computational physicist, and I know that this is what I did. And the reason is, if you put a job into the queue, you can estimate how long it's going to take to run. And if it turns out that you believe that by the time your job runs, you've already moved on to the next question, you'll think harder about what you put in the queue, and you'll ultimately limit what runs you do on the computer. The reason being, you have to be smarter about what you run. What the cloud does is it changes that. It allows you to take the jobs that can run in the cloud and get them off your on-prem system. It frees up your on-prem system to do the hardest work, get more value out of what you bought, and now you have a way to provide dynamic or variable supply to meet that variable demand. So we've talked to many customers who essentially say the cloud is allowing their engineers to unlock their creativity, unlock their productivity. And in fact, their biggest concern is how to contain how much they consume, because the engineers would consume potentially unlimited amounts of resources if they were allowed to. So this managing demand surges is really a big, big factor. Another thing that we see is R&D collaboration. More and more companies are becoming global. The data that they need to operate on can be coming from many places. What better place than to put that in the cloud and let everybody operate on the data together? Get a common view, do remote visualization. So a lot of people are adopting HPC in the cloud, again, to complement what they do on-premise for some of the really heavy-duty simulations in order to foster R&D collaboration worldwide. Obviously, easy maintenance is a key factor. You don't have to get your hands dirty. You can focus on your work. And in terms of capital and investment, it takes time to order and install a new system. And oftentimes, it'll be a new technology that comes out. And more often than not these days, the new technologies are showing up first in the cloud. So when the latest, greatest processor platform comes along, you may want that. You may even have an order to increase your on-prem system. But today, you can get into the cloud and start using it, understanding how your workloads behave, understanding what is the right configuration, because you can try a lot of different instance types to inform what it is you should be buying. And you can be getting work done while you wait for the systems that you've ordered to get delivered. Access to scale, the example I gave you of 1 million simulations run on 71,000 cores, that's just not something that you can afford to provision for those peaks. So complementing, again, your on-prem resources with something in the cloud that allows you to go and spike your workload when it makes sense and when it makes good business sense is a key value. And the last thing I want to say, it's not about upgrading current capabilities. It's about whatever you end up buying on-prem, there's value in making that as homogeneous as possible from a management perspective. One of the beautiful things about the cloud is no matter what you buy, it's been an optimized decision across a range of workloads. But there's always going to be one or two workloads that really wish you'd bought something else. Well, now you have the diversity of instance types in the cloud, and you can actually take those workloads that would have been better served by a different purchase decision and actually serve them in the cloud. And then you end up improving the match for the workloads that lined up well with the system you did purchase. So essentially, the diversity of workload types or the diversity of instance types in the cloud actually helps you optimize your workload mix. So Intel's Xeon processors at the heart of the Amazon cloud, and of course they deliver performance, and I'll show you some data about performance, looking at some of the latest instance types in the Amazon cloud and what type of performance they're delivering for high-performance computing workloads. But behind the scenes, Intel and Amazon have been working together for over a decade, engineering collaboration, delivering custom products to power the Amazon cloud to really enable the security and the agility that you experience through your interactions with AWS. So while we're going to focus today on high-performance computing, we don't want to forget that it rests on a foundation of security and agility that's coming from Amazon and Intel's partnership in this area. So the latest processor family that we released, it was about a year ago, was the Intel Scalable processor family. And these are the ones that we're actually recommending and most people are purchasing for high-performance computing. Compared to the previous generation, it improves performance on math-intensive codes, so floating point and integer type codes through this AVX 512 instruction set. And in fact, we get a peak improvement of 2x floating point operations or flops per cycle. And this is yielding performance improvements on real applications in HPC, as you can see, of 1.75 to 4.66 in the sample I'm going to show you. Obviously, you need to do your own runs and see what it does for you. But we saw very good performance improvements generation over generation on bare metal, and we saw those performance improvements translate into performance delivered generation on generation from the C4 to the C5 instance in the cloud. So if you want to use these latest processors, one of the instance types you can use is called C5, and this is actually one of the ones we recommend for high-performance computing. We've got more performance, and of course the price went up more slowly, so you have a 25% price performance improvement over the previous generation. We're using some custom Intel Xeon processors that we configured in conjunction with our partners at Amazon, and they run on up to 3 gigahertz. This is the Skylake generation, if you're familiar with our code names. One of the nice things in this latest generation is that you can actually access all the virtual CPUs on the system. So you can go up to 72 virtual CPUs and have access to 140 gig of memory. And this means you can do 2 gigabytes per core, which is a really nice, or per virtual CPU, I should say, which is a really nice amount of memory, especially for these throughput-oriented problems that tend to be more memory intensive than if you were doing a scale-out application. But it's still plenty of data, or plenty of room to run, of course, the scale-out HPC workloads. It's paired with a 25 gigabit network, and so this is actually now getting powerful enough that you can start to run HPC systems that aren't just that throughput-oriented set of examples I gave you before, but actually start running simulations that are multi-node. And over time, I actually expect that things like placement groups and reduced jitter, reduced latency, higher bandwidth, all these types of things are going to continue to grow in the cloud, and the subset of workloads that you can run in the cloud to complement what you have on premise is going to grow over time. So everything is heading in the right direction for HPC in the cloud. So here's some specs from the C4 to the C5 just to compare them. You see a doubling of the virtual CPUs. We've moved from the Haswell to the Skylake generation, which is a new microarchitecture. That's when Intel actually puts more performance out of the same instruction set and enables new instructions like the AVX 512. Giving you 512-bit wide registers that you can operate on, giving you tremendous parallelism for your math, per instruction. You can see the increase in the performance of the elastic block storage, and also the significant improvement in memory capacity. And while I didn't mention it, a lot of these performance improvements that are coming are actually coming through the increased memory bandwidth of this platform. So there's a lot improved stream performance, and about 50% of workloads in high-performance computing are memory intensive. And they're some of the ones that are going to see the biggest benefits here. And of course, the compute-intensive ones are going to benefit from the denser compute coming from the AVX512. So I promised to show you some performance examples. Here's a range of workloads. I hope you can read them. Some familiar ones here: stream, that's memory bandwidth, reflecting that 2x improvement in platform bandwidth. Here we observe 1.77x improvement generation on generation. Home, which is a climate application, climate and weather. Milk, which is quantum chromodynamics. Dyna, which is car crash simulation. WRF is weather forecasting. GROMACS and LAMPS, you see on some of the higher improvements up in the 3x range. Those are computational chemistry used a lot in medicine and other type of drug discovery. And then also DGEM there, which is dense matrix multiply. That's really showing off the double precision dense matrix multiply performance that you can get from the AVX512. And that's at the heart of a lot of algorithms. You see a 4x improvement from the C4 to the C5 instances. So just to come back to the point I made earlier about the diversity of instance types, maybe it makes sense for you when you're buying your system on-prem to build out these, say Intel, Xeon Gold processors. A typical model that people buy is something called the 6148, which is really great for high-performance computing, and is very similar to what you see in the C5 instances. But what if you have some applications that really don't benefit from large core count? Instead, they want a big memory footprint and they want really high clock speed. Well, we make those Xeons too. And even though you may end up not buying many or as many of those as you'd like for your on-prem system, they're always available in the cloud. So the Z1D high-frequency instances you see actually have 8 gigabytes to vCPU, so 4 times the memory. They can scale up to 4 gigahertz, so high frequency. So we see applications in electronic design automation, EDA, relational databases, sometimes in gaming where the frequency and the memory capacity is more important than the core count. So again, the cloud gives you the flexibility to augment what you purchase on site with the right instance type for your workload in the cloud. The last thing I want to talk about before I hand it over to Matt is, how many people are here at AWS, right? There's tens of thousands of people here. And many, many people who are here are working with the infrastructure level interfaces, right? But HPC users don't actually really know what to do with the cloud interfaces. Most HPC users are familiar with logging into a system. It likely runs Linux. It has a common environment across all the nodes. They can jump from one node to another, and they can submit a job that uses MPI, message passing, to run the applications they care about. And as you move into the industrial and commercial space, a lot of times the users of those applications, things like ANSYS and Radios and Dyna and some of the codes I showed before, don't even know how those codes work. All they know is the codes run on a certain platform on-prem. How do I run it in the cloud? And that's why it's critical to have people who are actually building a consistent HPC platform for the cloud that matches the environment that you see on-prem. Now, the hardware underneath is going to be different. It's going to be running on virtualized instances. It's going to have a different network. But from the perspective of the user and from the perspective of the applications, the fewer changes, the better. And the more automated it is, the better. And Intel's been working with the ecosystem, with Amazon, with Rescale, and with a number of other partners to ensure that the experience people get on-premise with their systems, the de facto cluster architecture is working today for HPC, is replicated in the cloud. Because that creates workload mobility and makes it really easy to do the things I talked about earlier, like picking which workloads based on their characteristics should be in the cloud and easily moving them without recoding, without rebuilding. And so with that, I'd like to hand it over to Matt, who's going to talk about what Rescale does, which is Rescale's a company that actually creates this layer and gives you access to those applications. Thanks, Matt.
So before I get into what Rescale is all about and who I am, I think let's start with a customer story, because those are always the most interesting. So if I wanted to understand how the avian flu were to move through a locality or through a region, it would be contingent on a number of different variables: access to transportation systems, access to healthcare, hygiene, education, numerous variables that would actually affect how that disease would spread. And the models that I would need to build to understand how that disease spread through a population would ultimately, the more and more refined they would be, the more complex and the more computationally intensive they would get. And so a great example of a company that's doing this is called MetaBiota. And MetaBiota runs tens of thousands of parallel simulations on the Rescale platform, on AWS services, powered by Intel technology, to distill complex disease models down into quantitative risks so that governments and companies can make good decisions about how to deal with a potential bio threat. In doing tens of thousands of simultaneous simulations, costs, if you're doing this on premise, would be quite high. In addition, costs in the cloud could be quite high too. So another thing that MetaBiota was able to do was leverage things like the spot market to bring their costs down, which ultimately allowed them to avoid millions of dollars of IT and server costs, and to be able to deploy, be very agile and responsive to their customer base, especially as biothreats began to emerge. And so this is the kind of example that we see when organizations are leveraging the massive scalability of the cloud. And when we talk about, Bill talked a lot about why, right? And so I think the why, I love talking about why cloud. It's fun. It's fun talking about how we can think outside the box and new problems, explore new design spaces, and it tends to be just a more interesting conversation. However, I think it's kind of played out. Bill mentioned the great, already introduced it. At this conference, AWS is happy to tell you about all the reasons of why cloud. What Rescale as a company is really focused is on the how. Bill talked about some of the challenges. I will talk about some other challenges that when you're migrating HPC workloads to the cloud, from the user experience to the infrastructure to the applications, and how Rescale is dealing with those challenges. And whether you're using Rescale or any other services, those challenges still need to be addressed. You may be able to take those back to your organizations on how to do that. Tim Crawford is a kind of a CIO luminary that shares insights on Twitter amongst other various social media platforms. But this really resonated with me in terms of thinking about the why cloud versus the how cloud. There's a lot of reasons to do it, but actually how do we then do it? So I'm responsible for our business in North and South America for Rescale. And Rescale, oops, I'm going one back. I lost a slide, but that's okay. So what Rescale is we are the how to do HPC on AWS. And Rescale is a software company, and we build the software platform that Bill was mentioning. And we have been doing this since 2011, which was too early to get into the market for cloud HPC. But now there's been significant evolution. We've seen a major uptick in virtually all customer commercial organizations that are committed to the use of HPC, to include academia and government, are now thinking about how do they extend HPC to the cloud. And that's what Rescale is doing. And so I'll go through a series of challenges and what those challenges are and how Rescale is addressing them. So the first is the availability of applications. Organizations that are committed to the use of high-performance computing are typically using tens to hundreds to thousands of different applications, different versions, and a variety of different licensing schemas. If anyone has tried to get a license server to talk adequately to different Amazon regions of EC2, they understand kind of the mundane but very real challenge there, especially if you're trying to do it on a global scale. And so a variety of different applications. A lot of these applications, as I mentioned, anything from open source to commercial off the shelf, different licensing schemas that you have to work with, and then also different tuning requirements on different types of infrastructure. And what the Rescale platform is delivering this systems administration burden through an automated SaaS platform so that you can manage access, install, tune these applications on a variety of different infrastructures that AWS offers. Another challenge is running on the best suited architecture. One of the major advantages of the clouds is a lot of variety. And if anyone is familiar with HPC applications, you know that different applications, even different models, can run optimally on different types of infrastructure. So let's take Abacus, for example, from Dassault Systems. That is a fairly industry standard nonlinear finite element analysis code. Every different model that you run through that application could actually be optimized on different infrastructure depending on the type of model you're doing. So how do you create a seamless experience where you can take advantage of the latest Intel technology and take advantage of all the different instance types that are available, but create a situation in which an engineer can choose the best application for the best infrastructure? And how do you do that seamlessly? Again, through a SaaS-delivered platform, Rescale is offering a seamless user experience where users can switch in and out infrastructure for different models and different types without having to do any changes to the infrastructure layer. Another challenge is reliability and security. High-performance computing applications are typically the crown jewels of an organization's intellectual property. It's designs, it's the research, it's the R&D, it's the cutting-edge technology that organization is working on. So in the shared security model, we know that AWS is going to secure everything that's on their end, but in the shared security model, a good deal of that responsibility falls on to my organization, to my company, to my agency. And so the end-to-end data management, the network access, the certifications that are required, it's not just the security of EC2 and S3 buckets, right? It's the full end-to-end experience and everything that your users are doing on that platform. And so Rescale is addressing this, again, through an automation of a number of these best practices that AWS recommends for high-performance computing. In addition, obtaining the certifications so that an organization can be confident. And it's just recently announced as we will be also FedRAMP Moderate certified here in Q1 of next year. Another challenge Bill mentioned is the user interface. With an HPC user community, you have a wide variety of different users, some that are or prefer to talk to the matrix, right? So they want a full CLI interface. They want to talk like they're normally talking to a scheduler in writing their scripts for those scheduling scripts. And then you have the other end of the spectrum where users don't know anything about what's going on behind the application that they're using or behind the GUI of the application they're using, and then everything in between. And so how do you support a user base that's diverse? You need a simple interface for not only users, but also your administrators that are managing access and control and setting budgeting for all across the users of your organization. But you also need to be able to support the users that are used to very scheduler-like interfaces, that have scripts that are set up to work in their current on-premise systems, and that would really prefer to use no GUI interface at all. And so how do you support that wide range of users? And Rescale solves that challenge also. And then also accessing diverse data centers. With geographically dispersed organizations, collaboration globally is very important, as Bill mentioned. But then also, in some cases, you have to be able to regionalize data. And there are data privacy laws or restrictions that cause you to have to regionalize data in different places. So how do you leverage the global nature of AWS, but at the same time meet local data privacy laws, and then also enable global collaboration when it will help the organization? So Rescale has created something called the Scalex Platform. It's a seamless AWS HPC deployment, and it takes all of the complexity of delivering HPC from the cloud infrastructure, and it also mimics all of the on-premise components that are required to deliver HPC into one seamless, automated enterprise SaaS deployment of high-performance computing for an organization. It does this leveraging all of the AWS data centers and all HPC instance types that AWS offers. And so what Rescale's mission really is how to deliver HPC simply, securely, and robustly. In the shared security model, a portion of the responsibilities fall on organizations, such as shared security and compliance, systems administration, management and monitoring, productivity, workflow and tools, deployment user experience, and one other thing that has actually been critical, doesn't really fall into the AWS responsibility, organization responsibility, but after 7 years of doing this and helping organization, it's something we call final mile support. To make HPC in the cloud effective for an organization, where the user begins and the infrastructure ends, is typically where all of your problems are going to arise in supporting an organization. And that's typically the toughest problems for an organization to solve, because it takes knowledge and expertise in the application itself and how that application interacts with the infrastructure. And the problems that arise can be many. A lot of them user-driven, but everything from the inputs to the application itself that's running on it having issues. And being able to troubleshoot and solve these problems is a critical component to making HPC effective in an organization. Now, Rescale offers this type of support as it comes to our platform as part of our service. But if an organization is looking to do this on their own, that's a critical element that it needs to be solved and needs to be taken into account for deploying HPC effectively in the cloud. So why a software platform? And Bill talked about a software platform, but it's worth asking, is this really necessary? And at Rescale, we obviously think it is, and it's helpful for an organization. And one of the reasons we think it's helpful is because we can use economies of scale to help drive improvements in HPC-specific features that the HPC community needs back to our user base. An example of 3 of these features that we delivered in 2018, the first is hybrid. So deploying both on-premise assets and cloud assets under the under a uniform one SaaS platform experience. So as your jobs are coming in one way and then being dispersed out to a variety of different infrastructures. Another feature is high-performance storage, where an organization can dynamically create, manage, collaborate with, and destroy high-performance storage assets within that organization for high data throughput. And another is what we call end-to-end desktops, which is really just interactive HPC, where organizations can interact with batch jobs. They can pause, they can change parameters, and they can look at results interactively as they're being generated in their analysis. So looking at, coming back and putting this all together about why this all matters, I think all of us are fairly attuned to the cycles of mobile phone releases. We expect new mobile phones once a year, those of us in the tech community especially. And so one company, P-Semi, Murata company, is using high-performance computing in the cloud to verify and test front-end modules for smartphones. And they're able to speed portions of the design process by over 10x. So by scaling up and out, especially for electromagnetic simulations on Intel Xeon scalable processors such as C5 and R5, they're able to take portions of the design in what used to take 15 days, they can now do in 1 day. And so when you have this access to kind of scale, and when you have access to a diverse set of resources, and when you're able to refresh your technology on an annual basis, you're able to use cloud HPC as a competitive advantage. So to summarize, AWS high-performance computing on Rescale, powered by Intel, is instant access to unlimited resources, choice of architectures, applications available and tuned, applications selected and running on the best architecture, jobs running with no wait. And ultimately what this really results in is faster innovation, shorter time to market, and things like system utilization or optimizing for high system utilization, and queues and engineers and researchers making decisions about skipping portions of simulation because they're simply constrained by the amount of resources they have. That is a thing of the past. And organizations are, today, if an organization does not have a plan to at minimum extend their high performance computing to the cloud, they will be at a competitive disadvantage. So I hope that was instructive. We are here to answer any questions that you have. But thank you for your attendance and for everyone's attention. Any questions? That's a good question. So the question was about proprietary applications that an organization has. It's very common for an organization to have proprietary applications that they have written and are using for high-performance computing. And the Rescale platform, from our perspective, supports that. So there's a variety of different methods. We support all the container technology that's out there. Singularity tends to be one that we favor a little more, based on its ability to support high-performance computing and MPI applications a little more effectively. But we also support other container technology. And so there's that, and there's also the ability to simply natively install on a proprietary application and make a private release to an organization. So in terms of selecting the best infrastructure, our team and our technical support team for every one of our customers helps an organization understand the performance of that, benchmarking on a variety of different architectures, and then what admins can do is restrict access to certain infrastructure that is good for certain software so that users are using the right infrastructure for the codes that they have.
I think I'll just add something. Is my mic on or no?
I think it is.
It is, okay. Which is one thing I really like about Rescale and working with them is, and we didn't get into a lot of details here today, is that they're providing interfaces at different levels. Matt talked about the spectrum of users and their expectations. But if you just want access to something that looks like a traditional cluster and don't need any prepackaged applications and want to get in on that and bring your own app, you can do that with Rescale. If you actually don't even have the applications, maybe you're coming from a workstation world and you haven't used HPC in the past, the cloud is your on-ramp to give you access. And so the ability to sit at your workstation, which is probably a Windows workstation, and very simply take some simulation that you're asking a really hard question. Now it's taking 2 or 3 days to run on a workstation. Being able to put that into HPC is difficult from infrastructure, switching over to Linux, learning how to build and deploy a system, going out and getting the license, not even know if you're going to get the return on investment. Rescale makes it easy for you to actually take your workload, put it in the cloud, improve the value, and ramp into cloud. So there's the full range of offerings sitting on top of that infrastructure layer that comes from AWS. Makes it very usable. More questions? Yeah.
We're just playing around with dipping our toes into high-performance computing, maybe with a big one. Could you guys walk me through the 2 different paths that you guys were talking about? One is to use the cloud to prototype what we might end up getting on-premise, and another one might be using Rescale to do a Baywork cluster at the cloud.
Well, I think a lot of it comes down to the expertise in your organization. If you have the expertise to build a system and you know you have enough workloads that you're going to keep it busy and you can achieve scale, then going on-premise can be quite cost-effective. But most people, when they're getting started, find that the software licenses may be too expensive, that the cost of an administrator get amortized over the number of nodes you have on-prem can be quite high when you're getting started. And so the cloud wasn't an option in the past, but now it's a great way to get started and start to understand the economics. And then you can decide whether you want to go with the cloud only, bring it back on-prem, or what most organizations we find is the optimal solution is a combination of on-prem and in the cloud. Matt?
Yeah, so to perhaps answer the question in different tact, I think you can use it for both, right? So it's certainly, you can use the cloud to prototype new technologies, inform purchasing decisions, in addition to inform purchasing decisions on scale, right? So it's, you may, through your testing, realize, or through use and through like a hybrid scenario like I discussed, you make more informed decisions about how to size on-premise versus cloud infrastructure. What we typically recommend is not, and the reason why we say extend and not replace HPC, right, in the cloud, extend to the cloud, is because there are workloads that do make sense to remain on-premise, especially when you get into data gravity issues and large data loads. There's certain workloads that simply make sense depending on where that data starts and ends to retain on-premise, and there's certain that make more sense to do in the cloud. So helping to draw that line in between, it could either be to prototype a new system, a new process, there's organizations that we work with that use the cloud for basically all their methods development. So they don't want to tie up production resources for all their methods development. So they have an entire group that is simply using the cloud to do engineering methods development. Then they'll deploy those methods down to the organization. But we're talking about really large optimization methodology and testing out how big, how complex they want to do. They want to develop these methods for, and then put it down to the organization. So what looks right for every organization looks different. But the common trends are what Bill referred to in terms of really eliminating that, the large queues, enabling access to be able to think about problems differently, access to scale, et cetera.
Yeah, there's nothing more expensive than an engineer sitting, tapping fingers, waiting. You're paying that engineer every day, and it costs a lot more than a computer. So you need to unlock that productivity. Any more questions or comments?
In ours or our customers? I don't have the answer off the top of my head. I might have to pull some specific.
So is the question, what's the largest kind of R5?
That we've run simultaneously in terms of, well, we know that the one use case that I am referred to was running about 3,000 simultaneous cores. So now I understand whatever your take vCPUs and then go down to physical cores and then divide, you'd be about there. I don't know the number off the top of my head if someone has R5 off the top of their head. Yeah. We use a variety of regions. So one of the, I think, a benefit of using a product like ours to be able to do high performance computing is that we have the ability to spread and push jobs. This is obviously not the tightly coupled job, but let's say we have 100 jobs of 100 cores each. We're able to hit and spread out those jobs and hit different regions simultaneously and then bring all the data back. We're also able to do that with spot markets so that we can read spot market levels, see where the spot market levels are in different regions, and then deploy resources out to different regions. So if we see like really high utilization or lack of resources, we'll dynamically move jobs from one region and push them to another. And so we don't have to do that, of course, if a customer prefers to be in a particular region. But that's with the particular use case that I used. If you are running into resource limitations and you're finding that one of the things we do is dynamically spread jobs. Yeah, and so, yeah.
Okay, so the comment is that you're having trouble getting the number of R5 instances you need. Unfortunately, that's something we'll need to take back to the AWS folks. That's outside of our control. Yeah. I'll take that back and try to understand what's going on. Yeah, it surprises me, but unfortunately, I don't have any access to statistics on instance counts or types. All I can do is take that information back for you. Question?
I'm sorry, GeoCloud? I'm not familiar with it. But is it all is it the public data that Noah put in the access? Yes, sitting in a public S3. Yes, we do. Yep. So we can do any kind of bring your own data stores, whether it being cloud or on premise, hook on any public data sets. So yeah. Yep. Monitoring applications. So we have some proprietary technology that we've built for monitoring the running of a job. Individual applications have a variety of different monitoring capabilities that we're enabling through providing either like interactive like head nodes on a running cluster or attaching a visualization node to a running cluster to be able to enable application monitoring. Does that answer your question? Okay. Yeah, so we actually, we utilize 30 different AWS services in delivering our final result. So we're leveraging heavily kind of all the innovation that AWS is pushing through our services, and then constantly updating our platform as a result.
I think we had a question up front here.
So what's the normal way or the preferred way? The data is moved from my cluster to the Rescale resource and probably more importantly back after it's run.
Right. So the methodology that we are using is we're moving it, so it's being encrypted. The moment that you're doing an upload to a Rescale managed S3 bucket, it's being encrypted. Moving to S3 bucket is a staging area, and then being moved to a EC2 instance. At that EC2 instance is being decrypted, run, monitored, then moving back to a S3 bucket when it's done, or when it's as the job is running. And then it's a user decision whether they want to do post-processing in the cloud, depending on how large the data set is, or they want to bring the data set back down or parse the data set in some way before bringing it back down. Does that answer your question?
Kind of. So is Rescale providing an API to write that into my submission scripts and define what I want to come back?
All of that is, so with the more complex workloads, yes, you can basically define the flow as you want. By default, that's the default though. So if you were to, in a very simplistic way, if you're a simplistic user going through our interface, we're going to orchestrate that all, like, or we're going to automate that entire process for you. Your command line user, by default, we're still going to automate that entire process for you. If you want like a specific different type of data flow, then we would just work with you to determine how to do that, like a multi-step workflow or complex workflow. Like some of our genomics customers have much more complex workflows where it's multi-step. We can script that up in a different way, but yes, it's not done as it's not done through the default submission mechanism. I'm probably not totally answering the question to your satisfaction.
And even in a typical, say, a CAE type application, your input data sets might be relatively small, but your output data sets could be quite large. Suppose you're doing, whatever it is, heat transfer, and you've got lots of time steps you've saved. A lot of times people will actually do their post-processing analysis and some visualization with the data in the cloud, doing a remote visualization, and then out of that decide what data they ultimately want to bring back on-prem and which data they want to discard. Because moving data, of course, is expensive in terms of time and also actual cost, right? So a lot of times it makes sense to look at the data in the cloud and then decide what to do with it. Yep. Another question here? Hardware simulations, okay.
How much performance do you see between bare metal or special ownership, especially the 5 instances Xeon E versus bare metal, especially Xeon E?
Okay, so the question is, what is the performance penalty of running in a virtualized environment versus bare metal? The answer is it depends, and it depends in a couple dimensions. There is going to be a performance penalty of running virtualized versus bare metal. And I think the actual penalty will vary by workload, and you can take your own workload and go run it. But it's typically measured in a percent or two type. That's the order of magnitude. What happens then, though, is you start to collect up multiple nodes and harness them together. You can actually see the gap between bare metal performance and virtualized performance growing. That's because you're introducing jitter and variation. You're introducing variations in the network performance relative to what you maybe would have purchased on-prem. And that's why if we think of this world of the range of HPC workloads, and this dimension being the sensitivity of the IP, you have to get comfortable with all the security before you put your data in the cloud. Matt talked about the security certifications AWS has and that Rescale adds to. The other dimension is the coupling of the application. And what you find is if you push an application too far out to the extreme, it will ultimately slow down rather than speeding up. And where that rollover happens in the cloud typically occurs before where it would occur if you built a dedicated system on premise with bare metal and a tailored network. So it really comes down to understanding your workloads and putting them in the right place. But the reality is that I've worked in HPC for 3 decades now, and I've worked at multiple supercomputing centers. I've never seen a supercomputing center that is actually running just the one big job that uses the whole system. there's always a mix of the big jobs that really drove the specifications of that system and a wide range and a long tail of applications that are smaller, which are these parameter studies. And so if you pick the right workloads and put those in the cloud, then their sensitivity to the overheads of virtualization and not being on bare metal are very diminished. And so it's still a good value and good business return at the end of the day. The examples Matt gave you, the example I gave you, these are people who really did get more work done in the cloud, and it was more cost effective to do it in the cloud because they picked the right workloads. So I think you'll see those characteristics change over time, but today there is still a bit of a penalty. So the question, if I understand, is: are there any plans from Intel to address the performance, to increase memory bandwidth and help out applications that are bandwidth intensive? Absolutely. I mean, one of the challenges in system design, of course, is balance, right? It's all about bottlenecks that you move around. And if we make a processor much faster, but we don't improve the memory bandwidth, then those applications end up not benefiting from the platform. Meanwhile, if we increase the memory bandwidth and get ahead of a lot of applications that were really dense compute, they suffer. So what you see is we inch these up over time. So in the example of going from the C4 to the C5 instances, we doubled the memory bandwidth of the platform. And I'm not making any public disclosures today about future Intel platforms, but I will say that memory bandwidth is critically important for HPC, and we have an aggressive roadmap to continue driving that up, and you'll see that delivered through the cloud. All right, one more question here. Like elasticity, right?
Yeah, so you're talking about dynamically, like during the running of a job? During the execution of a job, typically that's limited by the application itself to be able to do it. If the application supports it, a scale up feature, then we can support it. But typically that is an action taken prior to the selection of the resources. What we enable is dynamic selection of the right resource, the right application to run a specific job. One of the things I did not bore you with in this was what we did last year was a demo. Probably should have done that. And that is, it shows the ability to basically choose the resource and the resource size that you need for a particular job, for each job, for every time, as opposed to having like a fixed set of resources and then just submitting a job to some kind of subset of that fixed resource and then basically overspending.
Yeah, also, I think it's important to consider that the word job means different things to different people. Someone might think of a job as an individual simulation that's going to run, but someone else might think of a job as the collection of 1,000 different parameters that I want to sweep. Yeah. And if you have that type of job, which is a throughput-oriented job with many different things, then a cloud can be very elastic. It can expand out as long as it's keeping things busy and it's finding the spot instances and then contract at the end. But the individual simulations, if you consider that a job, it's very rare to see those expand and contract even on premise, let alone in the cloud.
Do you have a sense for whether you can build an HPC using pure S3 S3, or do most HPC solutions involve using like a high IOP EPS for all the transactional work? For example, we do image processing and we'll download like multi-gigabyte source images, and we're playing back and forth with the idea of whether to put it to a high IOP versus just keeping it in S3.
So when I talked about high performance storage, that's exactly what we're doing. Is we basically built a mini service to be able to dynamically create, basically a high throughput data storage device that you can hook up to multiple clusters, visualization nodes, et cetera, transit in and out of permanent storage, et cetera. So the answer is yes. The issue always comes down to cost, right? Because it's just expensive depends how long you need to keep it up. And so one of the things that we focused on was how do we make this the most cost effective as possible so you could spin it up for the least amount of time, get the work done, collaborate as necessary, but then constantly remind people that it's up and it's still holding data and you need to shut it down because you're incurring costs because it's basically like a running cluster for you. And then also putting like fail-safes in it so that could shut down over a course of time. But to succinctly answer your question, yes.
And the default in high-performance computing is applications interact with the system through file access interfaces. So bringing up a file system based on EBS is the kind of straightforward, most natural thing to do. And going through an object interface isn't very natural to HPC programmers. So you won't see a lot of applications out there that know how to deal with object interfaces, or any cloud interfaces for that matter. That's why they want to sit at a familiar platform interface. To Matt's point, one of the challenges, just as we talked about, it takes a certain level of scale on-prem before it makes sense. You have to have access, amortize the cost of the administrator, amortize the cost of the system, amortize the cost of the licenses. All of those have to get to a certain scale before it makes sense. And for many organizations, HPC on-prem does make sense. That is your entire market today, right? It's been built around that. But high-performance parallel file systems are exactly the same thing. A cluster system in the workload mix has to reach a certain threshold before it makes sense to dedicate a high-performance storage cluster. And just as once you put that gear on the floor, it's costing you, the same exact thing is true in the cloud. We can spin up Lustre and other high-performance file systems in the cloud, but as Matt said, they're just an additional HPC job that's running all the time. And the question is, do you have enough workloads to hit on that storage and make it worthwhile? All right. I don't see any more questions. Thank you all for coming, and thanks for sticking around and the great questions.